probably no one of us was around at that time because we faced back a few years. So it's a pleasure to have him back. So we had a chance to catch up. And also another important connection, we have been running together, and also maybe some of the people have been around. We had a joint DFG NSF project. So one of those projects are funded in Germany, and then there is a sister project from the United States, in which he was involved in his group and also in my team. And well, we had a lot of links and connections. We were talking how we could build more in the future and continue this cooperation. But yeah, so the presentation today is a good moment to see what happened in the meanwhile in West Virginia. Anurag, it's yours.
Nice, thank you so much. Yeah, it's my pleasure to be here back again. Yeah, in the year for third time. So today I'm going to more talk about physics-aware machine learning and how we can integrate physics into machine learning, solving system problems. Right. So in this one specific, we will all be looking at like PMU data anomaly detection. Yeah, what's it?
You try and for that one.
There's a top
Top of the right. Top there one.
Yeah. Sorry. Yeah, so today I'm going to talk more about how to integrate physics into machine learning, solving the system problem, specifically for the power grid resiliency. So power grid resiliency, now not so much new term. It used to be new term like 5 years before, and it basically means, so if you think about power grid performance, of course, one is stability, one is security, one is reliability, which we focus on, security with some failure and reliability with no failures. While resiliency is in extreme events, like there's a big weather event, hurricanes happening, or there's a big cyber attack. So if the grid is resilient, then it will still keep supplying power to at least to the critical load, not all the load, because it's in the grid system operation, we cannot provide power source. All right, so there are a lot of these different concepts here, but before we talk about resiliency and physics-aware, like to that, if you think about how do we solve any system problem, right? So we look at system and we start modeling, right? Whether it's a biological system, a physical system, or like power grid, which is cyber physical system. So what we do that we observe the system for a certain time period, and we see that how my input and output that we want is related. Then we form an equation, right? We all know that when we try to do this, it is only representing certain behavior. We are, like when we model the system, it's modeling certain. And then sometime linear, and sometime we get to higher order. This is like second order equation. And because we know that this is only representing a limited behavior, and the system becomes more and more nonlinear, my model is not going to represent, right? And that's what is happening. So in the power grid, as we integrate more and more digital devices, as we integrate more power electronics, it is becoming nonlinear. So our system equation will either number of variables explode and we cannot solve it the complete. And then we start looking at the data. Right? So okay, there's a lot of data, measurement, everything is coming. So with those data and network system, what we can do better. And these data were possible because we just put more sensors. So finally, we got this set of equation, we got a lot of data, and we know that this set of equation is not going to represent the behavior for a very, very large interconnected system. Right? So then we started looking at data because the data was not available in the past, but now we have more data. And then we started looking at the approaches like machine learning, data analytics. And then we realized that machine learning might produce results, which is a result from what we tell machine learning to do. And that might give us result which is not physical. Right? So it will give us output, but which is not even following physics. And this happens. There are multiple examples that we can talk about. So now the problem becomes that how do I'm still solving a loss system. If I have a small system which is well behaved, can be represented by a system equation, that's first preference, right? Because we have a set of equation which is representing the behavior, and I can analyze that. But if we have a loss system, we are not, going to work, and we have a lot of data. Then we apply machine learning, and then we also want to integrate the physics, so we still can solve a large scale system problem by integrating the physics into machine learning and getting our system analysis problem solved where this will not work and just the data will not. Okay, so it's a subset of problem that we want to solve. And we call it physics informed machine learning. Some paper call it physics aware machine learning and physics integrated machine learning, right? So there are different names. So here's one example, which is done by Ben Mosley, and very well present that. So it's very simple spring with the mass, which is like a harmonic oscillator. And if you try to solve with the equation, you can, right? So this is not a good example to even apply neural network. They can easily solve it. But if you have interconnected millions of spring, then you want to solve it, then your second equation is not going to work, and that might be machine learning will be better. So we solve with the neural network. It takes some steps, but it never converges, right? Because machine learning is not guided by a set of equations. And then you integrate your physics into neural network, and then you see the lower part, it is able to convert. And so if you go onto this website, you will get a set of equation and all the code for free, which demonstrates this problem. Again, with knowing that machine learning should not be applied for this simple problem, but as you scale it up, the physics informed neural network will still work. So now if you look at all the different set of data and system problem, then we have sometimes more data and less nonlinearity, sometimes more data and high nonlinearity, which is the most challenging problem. But if we have a lot of data and large scale problem, it makes sense to apply machine learning. And if we have a small set of data, but still not very highly nonlinear system, then we should apply physics-based modeling equation. Okay. So now we talk about a power grid and how we can apply. Can you really quickly? So with the system in the power grid, as of course, we all know that we are integrating more batteries, more wind, more solar, and distribution system is becoming, with all this automation going on, a lot of digital devices. So we do have more data. We do have a scalable system problem, and it makes sense that some of the set of equations which is not applicable now because it cannot take the same scale, some of the problem can be solved by machine. And then the problem becomes how do I integrate my physics into that machine? Right, so DR being integrated, microgrid is being integrated, microgrid management system is there, and we are trying to solve all these together to analyze the impact of the society, which is to go from one point really fast and impacting multiple different regions. So of course, grid changing digital transformation is happening with automation. We do have a lot of sensor data as we integrating, more number of micro PMUs, more number of smart meters, smart transformers, and all these monitoring and control applications. We can think about which one we cannot do better with the set of equations, and that's where we want to apply machine learning. Turns out EPRI has been working on this. Of course, a lot of organizations working on it, but I like this slide because it's talking about data on this, and then how we can apply. So first, what kind of data is available? So we do have a, data which is coming as an image because it's taken by a camera for the TNT, set a transformer. Then we have a measurement data like AMI data or power quality data, which is not streaming but lying somewhere in substation. Then we have satellite data. So there are so many different kind of data. Some are set, some are streaming, some are non-streaming, some are structured, some are following standard, unstructured. And then there are very high speed data, and then there are slow data. So all these set of data is there with the different platform, which we're not looking at together. And just think about that. If you open this, and it's already happening, if you open this data from the real system with some labeling, some manual work done already, and open to the AI community with the problem, and let's bring them together and say that what and with the problem, and let them solve it. Of course, we will probably have a better solution for somewhere our model based can solve. So with that in mind, let me go in each of these ways, one by one. So first thing is that why do we need AI-driven tool? And we already talked about that grid is changing, and especially the distribution system, which we need to solve in a scalable way. And if I need to analyze impact of these events, which is at large scale, we are talking about large scale problems, right? Especially with the cyber attack, which we cannot detect because they are trying to hide, but we still need to analyze the impact of where the attacker will go next. So that all tells us we do need more tools, advanced tools, which will help operator to make a decision. Right? Because as these things are happening, either we make an autonomous decision or operator make a decision based on a set of data. Autonomous decision comes with cyber vulnerability itself, because attacker can slice that. While human in the loop with the well-supported set of data and analysis will probably be better because then the human will make this, right? And with all of these set of data or problems we are thinking about, we already talked about reliability, economics, stability, security. In this whole paradigm, we do the same thing, which is basically get the data from the system, which is substation, transmission line, collect it to the substation control room, which will from the measurement, and then we communicate to the control center, and then we observe them, make some analysis, fills those missing data, and then do the control action. Of course, there are a lot of local control there too, which is embedded into the substation or into the distributed assets to do the frequency adjustment. The two things which is very important is situational awareness, knowing that what's going on in the system. So if there is a, let's say cyber attack is going on, how do I detect that when attacker is coming? Or if a hurricane is going on, how do I know that what it's going to impact? What are the chances that it will impact? Right, or snowstorm or anything. And then if I know the impact, I know the system status, then what I can do for the decisions. Okay. So how I can help? This is with Sigre group that I work with 2.52. We just almost finished our report. Of course, it can do the proposing action, prevent failures, provide more insight, especially prediction into the future. So we came up with this whole diagram, which is existing in forecasting control, maintenance. Of course, it's not a complete thing, but some of the examples where the AI can be, and there are use cases in the report for each of these. So, but there are challenges in applying the AI. So one is data limitation. Even if we have a data, how do I know that how accurate it is? So one thing that we work a lot, so I also work with the Pacific Non-Conditional Lab as a secretary, and there we do have a lot of data. We have a better collaboration with utility, which send us data. And a lot of time we have data, but we don't know that what anomaly I'm looking at, what event I'm looking at, because it's not labeled there. So I get this, but then I have to work with that specific utility, the materials, work with them, and it's been like a 6 month or 9 months just to get one substation data for a year level, that what happened on this day, and get some confirmation. So those data are, in some way it's incomplete, it's not useful, because I don't know that if I say by analyzing this data that this happened, we don't know the truth behind it. Sometimes I need data and also the network behind it, assess behind it. And those are not available because of certain confidentiality reasons. So data is in terms of insufficient or being inaccurate, of course, is very important. If I use inaccurate data, my machine learning will, also give the inaccurate view. Then the bias limitation, which can happen in the model, cognitive bias, or in terms of rapid diagnosis. Technical limitation of any machine learning is that we can, if something is happening, we cannot explain why it's happening, because there's no set of equation there to proof or showing that why it's not. And transform learning, we have to be very careful that when we take from one problem to another problem, and then how do we do that in terms of context. Right? So in terms of power grid, again, with the security group, we worked out that there are different requirements for AI using this application. So coming up with template AI is not going to work, because very much in the context of the problem you're solving. ICT requirement in terms of getting the data and storing it and securing it is of course a problem. Validation, I think we should spend more time in validation compared to doing development, because if AI or machine learning performing for, let's say, 10 scenarios or 100 scenarios, what is guaranteed that it will work for 100? The next 1,000. And that part you only prove by experiment. It's not like theoretical proof of equation based modeling approaches. So here we have to really do a lot of time on validation. Applicability in terms of long term or lifetime, and also expecting that like how machine learning and the data problem will be still solved with the same server, or what will be the need in future. Then there might be some ethical constraint, which is again for any other problem too, which we need to be applying. And here another thing is that where the data is coming from, who has the jurisdiction over those set of data, and when we use it, who owns the result? It means changing. If something bad happens, who will be responsible for that? That's so in terms of again system problem that we want to solve, if it is the application is very complex and the task repetition is in terms of very high in terms of scale, then neither model nor machine learning is going to be very useful. But if there's a lot of task repetition and application is not very complex, then of course machine learning will be very, very effective, right? So they can even do better than human. If there's no error they will make, it's a repetitive process, right? If application is complex, while like making decision for something they have never seen, and machine has not been trained, humans are still better. And so we can make a better decision for those scenarios which we have not seen in the past, especially if you're experienced. I mean, you can inexperience or experience will also affect performance, but on average, it will be typically better than machine learning. And if it's a it's not a very high skill problem and application is not very complex, then of course both. And somewhere in between, which is ideal thing, that's where I think we are in terms of hardware, that machine is augmented units, and that's why we integrate so many computers into the target operation. So let me stop here a little bit, and then is there any questions? All makes sense?
First, I really like integrating machine learning with physics. Is there a specific application we're looking at of this method?
Yeah, so there are a lot of possibilities, but we are looking at more like an anomaly detection, where I can differentiate between one anomaly to another anomaly and classify it. Because if it's following a certain set of physics, then it's PV string error. Or if it is following another set of physics equation, then it's fault. Or so that's what we are applying for. And that's what I'm going to talk actually next.
Okay.
Yes.
Maybe one more type of naive question. So one of the very first slides you showed the spring example. Yeah? So when you have the equation, then you integrate it into the model. But where's the trade-off? I mean, if you already have the model of the equations, you don't probably need data or the machine learning model itself. So it's enough to have like an approximate version of the model. Is that what you're saying, basically?
Yes. Yeah. So if till our set of equation is working, we don't need machine learning, right? But we know that, and we already know, like if you have a, let's say, 10,000 bus system with your fault lines integrated in the system, which brings this nonlinearity. And then you're trying to analyze the frequency behavior as things are changing. It will be challenging. We know that the equation will not be good. Even like in RTDS, if you model this, loss system, and then try to do the testing with high fault tonics devices integrated, we know that system behavior in the field and what we have modeled has already drifted. So till it's working, it's all good because it's explainable. It is, you can easily scale it up if the equation is still, application is still simple and system is not very highly complicated. But as it becomes, we see, even if you look at in the past, like a lot of these events, like especially in the US, that I'm aware of, like when the this big blackout happened, and then 2003, and before that there was a Western interconnection outage. There are a lot of graph that shows that how our model was saying the oscillation will shape up, and how in the field it was different. At that time, it was HVDC line. It was not well modeled in the system, while it was, of course, it was behaving the way it should behave in the field. And that's why there was a big difference between the oscillation, which was supposed to die out in the model, but in the field it did not. And so that was some example that happened in the past that shows that our model has limitations and cannot represent the true behavior.
And this now closes this kind of gap. Right?
Exactly. Yeah. So once we hit the limitation on model, and we have a data. If you don't have data, then we cannot go on the machine learning path. But if you have data, then we can integrate the model and physics and scale it.
So in this case, if you like the the final stage of the neural network would be the physics-based function, right?
Yes, yeah, yeah.
So instead, is there any models where you have a model before the neural network and it predicts something? I mean, with the model you get the data and then you use the AI to predict the error basically from the actual model to
Yeah, all these are picture and application are possible, yes.
So is it which is more effective in your research?
So in our case, we integrate physics into into the learning model of neural net, right? And it's only for the anomaly detection classification. But if I do some other application, maybe another model will be better. So as we we know that if we look at the power application, there's hardly any machine learning, right? Other than forecasting, we have not integrated machine learning anywhere, right? There is a lot of worry about that, how it will predict or how it will work in terms of control, which it has not been trained for, because in terms of heart rate, for large scale, we are talking billions of possible predictions. We cannot train the model for all those, set up those applications. But if we integrate into physics into that, then we know that even in those conditions, it will not give me a result which is violating the law of physics. And that's the advantage. But another examples with other example where AI and machine learning has been integrated, there has been always some hiccups, right? So it will take some time for getting mature. Even if you look at when we integrated computers in the power in 65, and it took a lot of time to the state estimation become mature enough to give us high accuracy. Forecasting of PV and which is still there's room to improve, but at one time it used to be like 50% or 40%. Now we are very close to 70, 90%. So there has been always some time taken for the technology to become mature. Either it's autopilot, which just in when it was reduced and now it's much better. Or the automation system in the car. And there was a lot of different experiments, including the test driver that happened in the past. And it has come a long way. We talked about these. Now, power grid is of course highly dynamic. So when we apply these techniques, data is again one of the limitations where it's coming from. What kind of data it is, what train it has, the continuous discrete, and then sometimes we also have data which is inferred data, which is not directly measured, or stress mission is estimated data, right? And PMU, which we call failure measurement unit, actually it's a failure estimation unit, right? Because estimating with the set of multiple linked, right? So it just depends on how we look at different measurement methods. But we should be aware that what's behind that, then only we can use it in therapy. So again, it's coming from transmission distribution, and all these are sets. Could be some market data, and different platform where it's going to that we want to integrate into. So all these details are necessary before we apply that. Now, some observation, which I think in some way we already discussed, that when we integrate the data, we need to be first make sure that our existing model is already hit its limit, and then only we are going to apply on this. When we are going to apply the machine learning or AI system to do something historical data, if it's not available to learn, then of course we can't do much. Although sometimes supervised method or performance is actually not that good as unsupervised, because we are dealing with very highly dynamic system, right? So unsupervised might be better. So it depends on application and basically the end user who wants to use that information and what is up. So a lot of different considerations before we choose the method, before you even first step, we even think about is machine learning is good here, right? And then the second step, then if we apply it, then do we have a good data? And then third, what is the AI or machine learning method is going to do? And the last, which is most important, is that if I do that, am I making the system more cyber vulnerable or improving? Because maybe by putting this whole data-driven with space integrated machine learning, you're making it more cyber attack vulnerable, which we don't want. So now let's talk about some use cases, which is again anomaly detection and event detection on this. So we have been working on this problem for a long time. We started with very simple statistical based approach, and then we started applying some machine learning, and now we are applying physics of machine learning. So we have developed some tools also, which is called Sync80, but the problem is basically you have the data which is coming from the measurement. You know about the system, which is network from the board. And you also have some data which is some streaming and some non-streaming, like like a fault with hardware will be non-streaming, but PME will be streaming, CTP will be streaming slower rate. And same thing for the cyber data, there are some event log which is not streaming unless you tell it to and parse it and send some data. But other data like network data is available all the time in stream. And what we're trying to do is that the status of the system. That if I see these set of data and I tell the system is operating as expected, or there are some anomalous or anomaly observed. If there are anomalies, what kind of anomaly it is? So this is the problem I'm trying to solve. And if I detect some anomaly, then I want to immediately send the alarm to the operator, or especially if it's hitting certain threshold. And and then I want to classify it so I can analyze and make some decision based on that. And we are calling all the anomaly, even like event, as anomaly, which means that some event which is expected, like line opening, because I open the line, is also anomaly. But I know that this is the known event, and I will classify that way. Okay? Even the intention is to find out those which I did not intend to. So line went out and try to open the breaker, I do want to do it. And then localizing it, because without localizing that what is happening and where, we cannot fix the problem, right? So, and then if event like cyber attack is happening, there will be multiple different anomalies at the same time, right? And I want to rank those. I want to know which one is more important to solve right now. And then finally, again, before fixing it, you need to take some quick action. But to find the permanent mitigation, I need to know that why it happened. What was the root cause? Then that's what will help me listen support. And then finally, to fix the problem. So if I look at all the data it's coming, of course, we look at CTP research package separately, PMU PDC separately, because these are coming in separate ways. But all start from the substation devices to some kind of sensor, and then some kind of data collection point at multiple level, and then coming to the application, right? So as the data is flowing, I can look at that, what can go wrong with that, and here's something that can go wrong. So if I see some anomaly, I will first try to find out is there any spatio-temporal correlation. If there is, then most probably, it's not, if there is, then it's event. And if there's no spatial and temporal correlation, most probably it's a bad day, right? So that would be one of the first classification. And then I can further look at, if it's an event, did we plan for that? If it's not planned, then why it happened? And then you can, make your way into the root cause. maybe those outage happening right now, or the fault happen on this line. So, or there is a sensor failure, right? So, and again, this is not a complete list, just like some example. And these things are happening in different layers. Some are happening in network layer, some are happening in physical system layer, some are happening in sensor layer, and some can happen at application layer too. So physics over machine learning, this is what we have been recently developed, and there are of course other literature too related to that. But in all of these, what we're trying to do is that we need to take the behavior, because we're saying this is normal behavior, this is anomalous behavior, right? So both need to be modeled, and we cannot completely model the anomalous behavior. So anytime we model the normal behavior with the known event plan, then we will know that anytime we depart from that, then that's anomaly, right? And also what is very interesting here is that what is normal now, like at this time, may be anomaly in the night when the load is less, because your operating condition have changed. So definition of anomaly is also changing, right? Because system is dynamic. So in terms of integrating the physics into this, there are multiple ways to do that. So one is more like a data dumping, which means that we take the system and we generate the data from it. And because the data is coming from the physical system, not from the model, then we can say that this data itself is representing the physics, because it's coming from the physical system, right? Which will be most probably the case, unless you use the model, which is only approximating the behavior of the system. Other one we can do is that we know the constraint in the physics. So the voltage should be between this the electric power at this bus should be between this limit. So when we are optimizing our training in the neural network, we can put the hard constraint in that. It might create a problem in terms of convergence, but that's one way of doing it. Right? Another one is this loss function itself. So typically, loss function is only looking at the performance of the neural network and comparing it with another iteration, and then trying to find out with the residue, then keep iterating by adjusting the weights of that was decided. So we can embed in the loss function, which is the equation. Again, there are some advantages and disadvantages in doing that way. Other, which is a little bit easier and does not create a problem in convergence of the system characteristic. So if I know the power grid network and I know the cyber network, I can model the neural network with similar network characteristic. I can embed the graph of the power grid with some weights into the GNN, right? And typically that works in terms of like for example in hard constraint we did face problem and they did not converge. Then we had to basically relax some and then decide that when to force and when to relax kind of constraint. So tricking the neural network to converge. Well, typically with the GNN, by integrating the graph, we were able to localize and characterize at the same time. It has a graph, so we know the node. So these are the 4 things that we tried, and then in terms of vectorial view, this is a neural network. Then in pre-training process, which means that we have a data from the visual system. We will use the data, which is resolution from the physical system model. It says model, it will use the physical system. That's data dumping. The second one will be the integrating into the way we train that. The other one is loss function. Right? So in all these processes, we can embed, and then we can the fine tuning you will basically use the real world data and do the same thing to get the better neural network behavior. This one is so this one is your reinforcement learning. So if I need to convert the physics into reinforcement learning, I can directly do that by creating those phenomena. Right? There is a state and there is action, and then go back for reinforcement learning. So this will be more appropriate for application like control. So what we worked on is like let's say there's a power grid and there is a wildfire is propagating through your power grid. And I need to take the control action so that the impact on the grid is minimal. If I try to solve a set of equations and find out that what control technique I take, in terms of generation redispatch, sharing the load, or transmission line opening, just think about all these possibility and solving it in short time with a set of equations will not be good. While if I try to do that with reinforcement learning, which is already observing the system all the time, and then take the control action, it might work better, right? We are still, even though we are solving it for the last 3 years, but there is still room to improve. So we apply reinforcement learning to generate my control applications while keeping all of these variables. There is some fax device installed, there is battery running, there is a plates, and so far, even with Collins bus system, it did perform better in terms of timeline. Right? It will take action in shorter time. It will take as accurate a set of equation, not always, and that's what we're trying to do. So in reinforcement learning approach, which we apply to wildfire, we basically embedded this set of equation in terms of reward and optimal solution. All right, so going back to the anomaly detection, we started with this ensemble-based approaches, which integrated from very simple approaches, which is a combination of statistical-based approaches and based. Then we worked with Siemens and we developed this PAML net, which is using graph neural network to find anomaly with physics. We also use this graph-based physics into federal agency, which is the tool that we developed. And then finally, we use the federal inference for stability control. So what we are trying to do is that with the PMU net, we were predicting the PMU data in advance. That's so 2 steps ahead. And once we predict that, in our measurement, which comes out of the system, if it's not matching, then either the 3 possibility, then either sensor data is not good, or my prediction is not good, or there is a cyber problem, right? I mean, and if we classify all these 3 things as anomaly, and then classify that what kind of the root cause, I will be able to tell that this is an anomaly or this. But at the same time, if I can predict, the PMU data more number of steps, then I can even predict the stability. Okay? So that's what we try to, use the same method of anomaly detection, and with the classification, we can analyze the stability. That was the work done with PNL. So this one is very simple. We apply very simple, approaches, and then we know that none of the approaches are going to be 100% result. So we got some detected anomaly, and then we made an ensemble of those. And knowing that we do have none of the approaches will give you 100% result anytime. This all the tuning effort, doesn't matter if it's machine learning or statistics. and lack of training. Then we apply these to by replacing like television with DB scan or random forest, weather transform, or LSTM, autoencoder, GCNN. So we apply a lot of different techniques. And sometimes we like random forest is already example, so it is standalone, but sometimes we replace one of these with another approach, and then again make an ensemble of that so that it works better than each individual approaches for detection. So, for example, this one you can easily see that manually I can observe that if it is making like this kind of behavior dynamic. If it's a certain graph, then I know it's missing data on facts. But if you have hundreds of these sensor data for longer time periods, I don't want to look at manual, right? So this is what I want to do it through approaches. So we apply this ensemble technique, which could be physics aware machine learning or simple statistics based or clustering, and then we basically integrate all those things together to get anomaly detection. And here we wanted to differentiate between the event and bad data, so we apply very simple Crony analysis, and that if it is a event, then Crony analysis will tell me that it's a dynamic running window, and if it is not, then it will be bad data. And once I detected that this is the bad data, it's not a event, then I don't need to further process it, but just flag it, it's a bad data. If it's event, then I need to know that what kind of unit it is. Is it active power event, or is it active power event, is it a fault event, or and we apply this simple cluster change method with the graph technique, where we can localize and classify into this. Right? So there's a lot going on in the slide, but the approach is simple: the ensemble technique, then some technique to isolate the bad data with the event, and then classify the event with the subgraph, and then look like it. So you apply, standard entropy in that structure to more like a GPS generalization method. Right? So if you have a GPS the way to track the car, same way we track the event, which 3 PMU is representing that event. And that's how it will move. Okay, so now the next problem was data drift, which means that what is normal now is not normal later. So we this work was also done with the Siemens, and we apply this technique which is called dynamic data chain driven learning and continued driven learning, which means basically it's telling that my normal has changed. And why? Because we do have a model too, right? So with the model, I can predict that what is normal now, what is, and I need to change in our thresholds in our system. So in this one, we still have an anomaly detector module, but we also have a module which will tell that our normal has shifted. And we do learn that. That's why this is learning. So again, I'm not going to read all these, but the concept is not only detect that it's anomaly, but also detect that my normal and anomaly behavior has changed over time. So next thing was that if I detect that sensor anomaly is there and it's giving me event, then I also wanted to check with, is it because of PMU data bad or because of PDC data, which is the next step, right? And by doing that, I can not only localize the event and in the field, in the physical system, but also into the data flow or cyber domain. So this is what we did. We know that what can go wrong, which is all of these things like voltage meters, current measure, PD bias, CP bias, packet data, timestamp, GPS problem. So all of these we made a note, and then now with analyzing the cyber network flow, analyzing the physical network flow, we are able to zoom in into where it's wrong in the both the network, cyber and physics. And that correlation will basically tell us better that why it's happening. Right? For example, if it's cyber attack, unless something happened in the network, cyber network, or in the PAML or PDC, it is not possible to see the impact on the power grid, right? So with both the domain, I can analyze and exactly track that down. So now next, with generator dynamics, which was the most difficult problem to embed into our physics aware or integrated machine learning approach. So what we did is that we looked at generators set of equation and tried to isolate between algebraic equation relation and differential equations. And then we created two new sets in the neural network. And then we applied this differential equation cells and then algebraic equation cells. So which is that part, which is like a zip load model, will be algebraic equation, while generator dynamics will be differential equation. And now I have a template which I can put together as many generators I want, as many load I want, and transmission line, everything is also can be modeled into this one. With the ultimate goal being same, that what is normal and what is abnormal, right? So now, even with the dynamics in the system, my neural network will still tell it normal because we expect generator to behave in this way. So that was an advantage which was not possible with any simple, like clustering based or any other, like even applying simple LSTM kind of network, which is possible with these. So in this one, we are directly integrating the physics into the neural network design approach. And then with this one, we can, of course, detect anomaly, but we can also apply it to detect stability of the system. Right, so with some results, for example, this one deviation, two different buses, which is one is kind of departing of instability with another. Then we want to estimate that what is jumping in the system. We can directly apply this set of equations and estimate. So now we combine this graph neural network and this algebraic equation and differential equation cells. And then we were able to predict with a predictive inference about stability of the system with following timeline and predictive inference. And then we can also take some proactive controls, even if the stability is real stability is going to happen because I can predict that. And then we'll take some remedial action if still needed to fix the problem, fix this. So almost done with the electromechanical simulator, and we also wanted to check with limited coverage. We don't have a big, but still more like 39 bus system. So we wanted to check with that, and we did all the PUD, PDC, with actual from the field. Then also had NS3, so we can see that pattern anomaly while we did all the things that we developed on this. Some quick results. This one is showing results from the PMU net, which is the graph neural network with the data drift. And results is very good in terms of accuracy, most are more than 97%. With all the different possible things we did, like load behavior. And this is for PAML, so see that before training not matching very well. The before training, this gray one is actual behavior. After training, blue and gray is kind of almost together. So it's very similar to the spring, but this is much higher order equation compared to spring. And that means that this is normal. So if I generate view, then performance I can tell this. And this is for the federated inference for proactive stability control. So it basically shows that if I take the action in time, so this is no control action, and this is control, and this is by taking proactive before this. Just to summarize, in terms of different things that we talked about, that model works better if we are trying to deal with smaller system and less nonlinear system, and we do have a set of equation which works in terms of capturing the behavior. But if you're if it does not work, then we need a machine learning. And at the same time, you have to be careful that it is being applied when it's necessary and only if you have a lot of data. And you have a lot of good data, accurate data. And also, sometimes you do have equation, but it is giving me a result in 3 hours simulation. Machine learning can be in same thing in 2 minutes. Then again, machine learning becomes one of the reasons to apply machine learning. By integrating the physics, we make sure that system characteristic or output of machine learning is good, meeting our purpose, and that's what is important from the problem, especially if it's a complex and dynamic problem like Shannon stability analysis, even latency analysis. There makes sense. Validation is very, very important, and metric, that how do I know that my machine learning is going to give results. Right, so we'll stop here. And thanks again.
Your questions?
Yes. For the case of the PMUs and anomaly events, how do you create a situation that is bad enough to be a problem, but that would not be caught by usual internal PMU checks? So transient monitors, synchronization, quality indicators, etc. So what is the type of situation that is in between?
Yeah. Well, so sometimes even though if you can see it at the PMU, it is not propagated into the data packets, right? So for example, GPS logs, right? It should be one flag into the PMU data packet. So we can see that. But if the GPS is spoofed, then you cannot see in the PMU data packet. So PMU will not tell me, but then I have to figure out with this technique that it is not giving me as expected, so it's an anomaly, and anomaly is caused by GPS, which is a hard problem to figure out. But this will be one example of finding through the PMU in a known way or through the discipline. Okay, any other questions?
In the whole machine learning flow, from the inputs down to where you determine the analytics phase and your use case that you're trying to find, where are the critical points where there are challenges in applying physics-based method into the machine learning flow? And how can, I mean, it be explained or better done? For instance, like in the activation function, has it ever been a problem that activation functions are static and you have to put in the whole dynamic nature of the physics-based method? So where do you have such, and how do you solve it?
Yeah, so it depends on how we are planning to integrate physics into the, machine learning. So for example, it is only based on input data, right? So there's input data, then there's a, activation function, and then the optimization, which basically is giving the training. So if it's only input data, it's coming from the real system. And sometimes people claim that it's physics. However, machine learning, because no data is being generated for simulation, and all the data that is being used for training is coming from the real field, right? So that will typically not be very challenging to solve. But it does not guarantee. If you integrate into the network, which is a graph neural network, then again, it should not be a big problem. But as you get into the activation function or into the optimization, either by hard constraint or by objective function application, there the problem comes, because it just, any optimization, if you make it more complex and constrained, the possibility to converge become a problem. And in this one, it will become more problem because there are so many interrelated feed into it optimization. So that's why we, the idea of federated was that instead of solving a big neural network, we solve it smaller, and then federate it. So in that way, it can give us better solution.
Okay, and do you also see like a limitation in the physics-based method for, especially like for cybersecurity, where you have to deal a lot with non-numerical data, and when semantic situation comes in terms of, do you see the possibility of equations, however algebraic or dynamic, not being the solution, but maybe logical axioms that can be embedded to be able to give more inference to the whole thing? So is that a limitation, or do you see a situation whereby you can also combine logical axioms as part of the physics-based method of machine learning?
Yeah, no, I think we did apply in cyber. So in cyber anomaly detection, cyber data anomaly detection, if our simple approach is like, there's some certain set of rules or rule-based approaches can work, then we did that first. And then the other data set where we cannot apply it, which is more like a time series data, then we apply machine learning approaches to be.
All right, thanks.
There was a slide about the data acquisition and gathering. Maybe
Which one was that?
it was something about data gathering and acquisition, and the way you thought about we're talking about different kinds of data, like primary and secondary data and so on. Yeah. So my first question would be, what is actually primary and secondary data?
Yeah, so like direct measurement is a primary data, right? But the secondary data will be, which I can get the same measurement, like let's say PMU is giving me one, but then on slower frequency, I can also get the same kind of measurement from CP and PT. So that will be secondary data.
Okay. And then you click. So I was wondering, how does it, what is for you the consequence of where the data is coming from? So how do you treat those differently? So do you have a process?
Yeah. So that's a very important thing, because For example, the state distribution data, we know that it's not raw data. It is estimated, which means calculated. And if calculation is, or estimation is coming with high residue in the state estimation, which means that the confidence on those set of data is right. So this context is very important when I try to use that based on that compared to raw data, which is coming from indirect. Yeah, so we will be, knowing the context of where data is coming from, how it is obtained, how it is calculated, is important to give a different weightage into my monitoring.
So I was wondering more about in this in physics informed neural networks, for example, if you infer some data, whether you then give it a different kind of process, like maybe an observed data is more valuable somehow, or
yeah, so observed data will be I'll again, if it's inferred data, but I know that the inferred data is giving the process of estimating that inferred data is most probably highly accurate. Then I'll treat that in the same way. But if I know that this inferred data is a pseudo measurement without any metric to tell that how accurate it is, then I'll give it low weightage or I'll not even consider.
Okay.
I have a final question. Yeah. What's the difference between physics informed and the scientific machine learning? Are they somehow the same, or there are major differences?
Yes, scientific machine learning is more prioritized. Physics informed is kind of subset of it. Right? So you develop a machine learning technique and you're applying any fundamental or sometimes foundation. That will be scientific machine. A subset of that will be physics.
In terms of responsiveness of the statistical anomaly detection and the revision, do you find it more faster in terms of the time response?
Yes. Yeah. So most of these statistics based will be much faster. The computation load is so less that it will give you much better result, but at the same time, inaccuracy is also higher. That's why we made this ensemble so we can get a better accuracy compared to each of those. But we're still in 90 by integrating the statistics aware we have to 97, 98.
Just curiosity a little bit off, but are you also looking at generative AI and yes, which application?
Yeah, so we're looking at two. Right now in terms of projects. So one is looking at, if you think about these attacks, cyber attack that happens, sometimes it happens over several months. Right? And so if you think about cyber attack from step 1 to step 18 was resulted into generator updates. So step 1 was getting into the substation and finding the password or something, right? That was step 1. Then step 2, step 3, step 4. And some of these steps I cannot detect because there's no detection mechanism that I installed. So each step become a letter. And the 18 steps become a word. So now I'm trying to predict the next letter in the word with generative AI. While knowing that some of the letter I don't know, because I did not detect. And then it means that it becomes, if it's a 18-letter word, then it's become a million of combinations. So my generative AI can tell that you know the letter, third letter and sixth letter, and it can mean this. So I look for those possibility, but we narrow down approaches. Yeah.
What are you using in these projects as generative?
Yeah, so I mean, we're looking at, so we work with the AWS, their engine, we're looking at, I mean, even though these are free, but if I want to modify this cost money. So we have partnership with Amazon. But then there are some open source,
Which will.
Llama. Yeah, and then other applications we are looking at it for the same one, like anomaly prediction.
Okay.
With the context, so the token become context. Like it.
Any other question? Thank you again for the presentation.